conservative forces and constraints. But again, if you have non-conservative forces and constraints, that's fine, add them in. Okay? Deal with it exact same way as if it's an underground train. This is indeed easy, let's do it. This is M to MR dot. This guy, we need to do it carefully, because we have 1 over R squared down here. So this is P theta squared over M R cubed, and positive, I guess, right? Yes? And minus mg. So the equation that we get is R double dot equals, we're going to divide by 2m. So this is P theta squared over 2m squared R cubed, right? Minus m minus u over 2. Okay? You got a very nice equation. You could have lived with the r and theta, got an equation for r double dot and theta double dot, and then play with them together to get r. You could do that. But here is how to do it without further manipulation. Any question, please? Now, why this is useful here? It's always good to get an equation, single equation and single unknown, of course. Because the following: whenever you have your acceleration, whether it's x double dot, theta double dot, or r double dot, whenever you have your acceleration as a function of position, we can do interesting stuff. What? Acceleration is function of position. Acceleration means forces, because you simply multiply by mass, right? So it means that your forces is just function of position. Your force is function of position, so it means it gives you the impression that it comes from a potential. So I will define this as negative, this is the force, right? Negative dV by dx. But I will call this the effective potential because it's not the actual potential. So whenever you have your acceleration as function of position, simply call this guy, I'm defining it here, to be negative dV effective by dx. And integrate to get your v effective as a function of x. Okay, why is that useful? Because when you plot this guy or sketch it, it gives you a very good idea about the system dynamics. What? First, if it's the first derivative is 0, this is the potential. First derivative is 0 of potential means what? First derivative of potential means 0. It is 0. Means what?
Force.
Yeah, look at this from here, from the blue. It's very clear.
Constant.
The first derivative is 0. Means what? Equilibrium. The acceleration is 0. Means equilibrium. So all these points, the maximum and minimum, are equilibrium points. But it gives you further. An equilibrium point, what is the definition of an equilibrium point? An equilibrium point, if you start there, you will remain there indefinitely. Okay. But if you perturb a little bit from that position, will you come back or will you go all the way? This depends on the stability of the equilibrium point. Okay? So equilibrium and stability are different notions. Equilibrium means if you start right there, you will remain there indefinitely. That's fine. But now if I perturb a little bit from that equilibrium, will I come back, or just blow up? It depends on the stability. From this figure, you get the equilibrium, the first derivative, and also stability. If it's minimum, then it's a stable equilibrium. If it's maximum, then it's an unstable equilibrium. Okay? So the graph of the potential energy, or here in the effective potential energy, gives you all this information. So you can immediately get it from here, right? Acceleration is function of position only. I will call this negative dV effective by dr. And I will integrate it to get the v effective as a function of r. Integrate this term, please. Here is the negative outside. So this is p theta squared over, this is m squared r squared. and this is 4, this is negative, grid this term, negative g over 2r. So when you've got this negative inside, I have positive here and positive there. So you can sketch it, V effective versus R. You have a linear term, this is a linear term, right? G over 2 times R, something times R. Here is the linear term. And you have 1 over R squared term. Here is 1 over R squared, right? And you're simply adding them together. When R is very small, this guy is small and this guy is large, so your addition will go with this guy. And when R is large, this guy is small, this guy is very large, so your curve will go with that guy. And in between, it will look like this. So here is the plot or sketch of your V effective versus R. There is a point here where the slope is 0, right? So this is in particular an equilibrium point. And is it stable or unstable? Stable. So you immediately get the stability and equilibrium if you have a single equation and single unknown, and this is function of position. So the rule here was very helpful doing that. Let's continue next time.